This conference will now be recorded.
Good evening, everyone. Welcome to the fifth day.
Good evening, sir.
Krishna Jyoti, could you please be on mute?
Yes, sir. I'm trying. Sir. I'm trying, sir, but it is not. Give me 2 seconds, sir.
I will do it from my side.
Yes, sir. Thank you.
Uh, Good evening, everyone. So today we will be discussing the concepts on backstepping control and extended Kalman filter. I will just briefly explain what is extended Kalman filter. And tomorrow is the last session, so tomorrow we will be discussing about the extended Kalman filter. So how it is happening is slowly we have till now we have seen only the application of linear systems. And though the control is non-linear, still we discussed only about the linear systems or the linear systems, and we could able to separate the linear and the non-linear separately. Linear systems we can design, and the non-linearity we can either consider as a disturbance or faults or whatever it may be, and we can still work with it. So this particular aspect of backstepping control, what we are going to discuss today is completely based upon, it can be applicable to linear as well as non-linear. It can be applicable to generic systems. There is no such uh, limitation that it can only be applicable to linear systems or to the non-linear system. It can be applicable to any such system which is having certain structure. So today, the backstepping control, whatever I'm going to discuss is from this particular reference. That is reference number 1, TTK 4150 guidance and control of vehicles. So I will share you this reference by the end of at the end of this lecture. So the fundamental question what we have to ask ourselves before going to the next session is what to do with the reconstructed fault from an unknown input observer. We have studied yesterday unknown input observer. We have designed the unknown input observer for a system, and I think most of you have got. Could you please put it your response in the chat box? How many of you have got the exact results? At least to 25 to 30 people I have responded. They have sent their uncorrected file, and then I have corrected and sent to most of them. In some cases, I couldn't able to send them because their MATLAB version is Simulink version is very old or or very new. So 10 such percent cases are there, but remaining to 27 people, 27 participants, I corrected their file and I sent. So I would like to know how many others, how many of you have got the exact results as far as the unknown input observation. If you are giving the sinusoid of high frequency, you could able to track. So, could you please put in the chat box how many of yes, just write down yes, nothing more than that. How many of you have obtained the results for the unknown input observer? Ashwin Kumar. Amarendra, yes. Anu. People are typing in alphabetical name. Anand, it's good to see that uh, the people are there. If you are not able to get the results, so it is not a very difficult thing unless you have followed the previous lectures and how to, and if you have done the coding, so this will not be a very difficult thing to get the results. Okay. So okay, I can see that some of you have already got the results. Some of you have already kept in the Patna S Patnaik has kept the result in the WhatsApp as well. So okay, so we will continue our discussion. We will ask the fundamental question. So yesterday we discussed unknown input observer for state estimation in the presence of the disturbance, and we could see that our estimate we can kind of decouple the state estimate as well as the disturbance up to certain level, and we have seen we have estimated the fault as well or the disturbance as well, and we have seen that if it is a unstable fault or sinusoid fault with low frequency and high frequency, I myself had tested for around I think 250 300 radian per second, and up to 100 the fault level, so it is working very fine. And now the fundamental question is, what do you do with the reconstructed or estimated fault? Yes, we did the fault estimation and fault is looking very fine. So then what you will do? So what is the requirement? What is the practical requirement of estimating the fault? So yeah, the idea is like this. You have estimated fault, and if the fault is above the threshold, you set some threshold. And because if you set the threshold as 0.005 and you don't know whether this is due to the noise or due to the fault, set some threshold for a fault. So if you can say that, uh, if it is a boost converter, and if you say that if your current measured current, if there is a sensor fault, and if it is drastically going, suppose if the expected range is 10 amperes, let us assume, and if it is drastically going to 50 or so, or let's say 30 or so, so that 20, is the fault. So don't so what you have to do is you have to keep certain threshold. Threshold means that is the minimum value which is acceptable level, beyond which you say that okay, this signal is faulty signal. And once if you know there is a fault in either in the sensor or in the actuator, and then what you have to do is you have to disengage that particular sensor or actuator, and then you have to operate the system. There are two particular cases can appear. If you have redundant sensors or actuators, that means for a particular sensed value, suppose for a boost converter, instead of one sensor, you may be using three different sensors. So what you will do is, in general, what we in those cases, in some cases you even don't need the fault estimation. What you do is logical fault estimation, fault detection tools. What they do is they keep on comparing the three. If it is a triple redundant sensor, they will keep on comparing the values from the three all the sensors. If there are two ways. If the average of if average of the three sensors is going beyond certain limit, then you can say that there is some sensor fault. Then what? And another way of checking that one is you try to compare sensor one with two, sensor one with three, and simultaneously, you keep on comparing the values. And if you see that if two sensors are giving approximately, more or less the same within the acceptable range, and the third sensor, let us assume, if it is giving some nonsense value, then you can say that the third sensor is faulty, and you can disengage it. And still, you can use the remaining two sensors. So that is a way to do that. However, that is not always possible. That is always not possible to, based upon only the logical sense. Yesterday, the problem what I told that there was triple redundant sensors. There were no redundant sensors for the angle of attack estimation, and all of them got failed. Then what? Then what? So that comparison, that logical fault detection will not work in the cases. So that's why this fault estimation plays a crucial role. So, and the next thing is fault compensation. Suppose for the control purpose, if you know what is the fault value of a particular system, then they can use some kind of feed forward controller, feed forward compensator to compensate that particular fault. Suppose if you know the fault ahead by using certain estimation algorithm, then you can pre-compensate that by using, or if you have accurate fault information, then you can subtract whatever the value is coming from the fault, the fault-free state minus faulty state minus fault. Since the fault information is accurate, then whatever you're getting, you will be able to get the fault-free state. So suppose if your sensor has certain fault in that one, and if you know what is that fault, so then whatever the faulty value you're getting from the sensor, if you subtract with the fault, then you'll be getting the actual state as well. So that is one way of doing the fault compensation if you have the accurate fault information. And there are another things as well, so analytical or hardware redundancy. Hardware redundancy means you will be using, multiple redundant practical real hardware sensors, and then you will keep on checking, and you will see what is the one what it do. And analytical redundant sensor is based upon the residue, whatever you are getting. The residue means the actual minus the error, or based upon the fault, you can generate the residue. Residue means the kind of error, and based upon that error, you have several ways Is my voice is not audible? Ramesh Babu is saying that it is not audible.
It is audible, sir, but not clear, sir. Not that clear.
Not that clear. Huh? Okay. Okay.
Yes, sir.
So
Audible, sir. No
so
problem.
okay. Thank you. So the analytical or hardware redundancy are the things which one has to, if you really want to implement, some system for real life systems. It's not the laboratory prototypes or some small, tiny toys in the lab. If you're doing for that, it is not required. But really, if you want to take, if you want your algorithms to work for the real life practical systems, then one has to go for the, then all those things are very much important. You have, it should be fault free, it should be fault tolerant, and you had to, you had to use the concepts of hardware redundancy or the analytical redundancy for the robust fault tolerant system and so on. So that is the purpose of the estimating the faults by using the unknown input observer and so on. So that's what we discussed yesterday, and I can see that at least some of you have got the results. If not, try hard, and you put all the fundamentals required for the simulation have been given to you. But still, if you feel that you couldn't able to replicate the results for the unknown input observer, please send me an email with a request to what the problem you're facing, or you can send me the Simulink file as well. I will try to correct. Unless if you're sending very old file earlier than 2010 or so, then it will be a bit difficult for me. Otherwise, we can I can remotely check your computer. You can, if you give me the remote access to various Autodesk or various softwares are there, then I can online I can correct it from here. So that's about the yesterday's problem. And now today we'll be discussing a very important concept which is called as a backstepping. And now what I will do is I will show you before going to the backstepping, the concept of Lyapunov theory is very much important. And with this tiny example, with a toy example, I will tell you when can you say a particular system is stable or unstable and other things. How to analyze the stability of the system. It doesn't matter if it is a linear or non-linear. So we are slowly coming back. We are going to the non-linear systems. Till now we have discussed the linear, so this is a bit difficult than as compared to the linear system. So before going to that one, there is some relationship between the feedback linearization, what we have studied, and the backstepping approach. The concept of feedback linearization, what we have already studied in 1.0, FDP 1.0. So there, what the philosophy is there, you try to cancel out all the non-linearities and then replace it with the desired system dynamics. The problem there is, if you cancel all the non-linearities, some of the non-linearities may be very useful as well, and some may be useless. So what is the limitation there is, since you're canceling all the non-linearities, those non-linearity may have some useful non-linearities as well. I will tell you what is useful non-linearity, and it is okay to cancel the useless non-linearity and replace it with the desired dynamics. But canceling all the non-linearities is one such disadvantage or limitation of feedback linearization. So what is the problem with the feedback linearization? So that is actually the problem. So we will see, consider a nonlinear system x dot equal to minus ax square minus bx minus 6cx cube plus u, where I assume that a, b, c has positive values, a equal to 1, b equal to 1, and c equal to 1, and u is control input. Now my purpose is to design the control u such that it should give me a stable response. So first of all, we have to see whether if this x dot is stable enough. Is the x dot is by nature it is stable? Yes or no? That we are going to see with an example of with the Lyapunov theory. This is the a equal to b equal to c. So what I will be, okay, first I will go through this slide and then I will explain you this thing. So feedback linearization law is to cancel all the non-linearities and replace with desirable dynamics. So what I'm going to do here is, this is my state equation. So all of you can see that this is my state equation, x dot equal to ax square minus bx minus cx plus u. I would like to cancel all the non-linearities and the linear terms as well here. Everything I will cancel and I will replace such that my closed loop pole at minus 20. So what I have to do, I have to change everything. U is my control thing, which is in my control. I have to select U such a way that everything will get cancelled and it will be replaced with minus 20 into x. So this is the one. So I will cancel all of those things and just I will replace with minus 20x. So it is going to happen like this. So what is this u equal to x square plus bx plus c cube minus 20x. If I substitute this back here, then I will be getting x dot equal to minus 20x. So this is the desired. So this is stable system with pole at minus 20. So this is a quite a stable system. So now what I'm going to do here is I will show you this is a very simple nonlinear system, but still finding the whether this is stable or unstable. If it is simple linear system, yes, pole is on the left half of a string. You can assume it as a stable or so on. So the nonlinearity is coming from various factors. The square term is there. Whenever you see the square term, cubic term in the state, square term in the state, or sinusoid term, logarithmic terms, and so on. So during those cases, we can always say that the system is non-linear and it will not obey the principle of superposition and homogeneity, which we'll not discuss, which is beyond the scope of the book. So we will try to see how to find the stability of this non-linear system. Just give me a minute. I will just I will write and I will derive and I will show you with a simple example. Okay, I will stop my screening now. If something is visible to you, can anyone respond? If my hand is visible,
Yes, sir.
No, sir.
my hand.
Yes,
Okay,
sir.
Yes,
so let's start working on this one. I will start with a simple.
Sir, it is small screen, sir.
Yeah, is it the small screen?
Yes, sir.
No, you cannot make it big larger screen.
No, sir, not like screen sharing. Very small.
It is not the screen sharing what I'm doing.
You just write it once, sir. We will check once. We'll see.
Yeah. Can you able to see this one?
A little
It
bit blur,
is
sir.
clear, sir.
Yes, sir. It
Yes,
is
sir.
visible.
It is clear, sir.
Yeah, you can make it large, right? You can enlarge it, isn't it?
Yes, sir. Okay.
Okay. You can see in the big screen, right?
Yes, sir.
No, sir. We are not getting.
We cannot change the screen, sir, as it is a camera, no, sir.
No, you can see that. Not then what?
We are not. We are not getting anything displayed on the screen, sir.
Sir,
It is
it is
visible,
okay, sir.
sir.
Sir, visible, sir. It is
My
It is
hand is
visible,
visible,
sir.
right?
Yes,
Okay,
sir.
okay.
The x dot is equal to minus x.
Okay.
X1 dot is equal
Okay.
to minus x is visible.
Yeah, yeah.
It
Okay.
is not.
Okay,
Visible.
so
It is not visible, sir. Here.
it's not visible.
Please select active cameras, then it will be visible.
Yeah, you can select the active camera. Yeah. Is it visible?
No, sir.
No, you
Sir,
select the active camera. View active cameras.
if everyone else closes the camera and only sir displays his camera, then it will be visible.
Yeah, yeah. That you please do it. Ravi Kumar, please close your camera. Yeah, I think it is visible now, right? Yeah, I think it's visible now. Okay,
Sir, now
so
it's
now
fine.
let's start. Now we will try to derive x dot equal to sir Shashikumar sir. Yeah, we'll try to derive x dot equal to minus x whether it is stable or not. So first of all, plus u. Let's consider this is there is a u term as well here. So now what we will do here is we will consider a Lyapunov function for this. This is scalar one. You can see this is scalar one because there is only one such state. So as we have seen that v equal to half into x square will be your Lyapunov function. So control Lyapunov function. Some people say control Lyapunov function.
Sir,
So
window
what does
is
this mean?
very small, sir.
Sir, I think you have to keep the that option, sir. View active cameras. You can see in the top there will be view active cameras. Rashi Kumar sir, please switch off your video, sir, so that others can see. Amarendra sir, please keep your active cameras on. View active cameras rather than viewing everyone, viewing all participants. So what we are trying to do here is this is a Lyapunov function. Why we call it as a Lyapunov function? This is a positive definite function. Why we are calling it as a positive definite function here? Because if you use any value of x, whether x is positive or negative, since you are taking the square, v will always be positive. If you take v of 0, it will be 0. That means if you substitute x value as 0, it will be the v of 0 will also be the 0. So Lyapunov theory what says that in a very colloquial way, the first derivative should be negative definite for the stable equilibrium point. So why this half is coming into the picture, why we always take half, now it will be more clear. If I take the derivative of this one, if I take the derivative of this one, so what is this going to happen? V dot equal to half into 2 into x dot. The x square, so 2 into x dot. So these terms will get cancelled 2. So eventually it is you are left with x into x dot. Okay. So now x into x dot is the one. So eventually, so finally this one. So what you want this x into x dot to always be negative definite for the stability. So that's what the Lyapunov has told us. So what I will do here is this x dot, I will substitute this x dot, I will substitute from here. We'll see the beauty of the control design from here. So now if I substitute that x dot from here, what is going to happen? That will become x into minus x plus u. So what is going to happen now? This will become minus x square plus u. Even if I consider u as 0, even if I consider u as 0, due to the definition of my Lyapunov function, due to the definition of the Lyapunov function, my my v dot is negative definite, negative semi-definite, let's say, and hence the equilibrium point is stable. So you don't need exactly the control for this particular purpose. However, if you want to, so what is the physical implications in terms of the system? Here, if you see that here there is a 1. So 1 into x, that means if you directly translate it into the poles region, then your pole is located at -1, and hence the system is stable. That's what we have shown from the Lyapunov theory as well. We have shown from the Lyapunov theory is that for this, we know that this is stable by definition, because you are placing a pole at -1. So it is, you don't need u exactly to just to have the stable system. But if you want the faster response, for example, if you want your your poles to be at desired one is, I will say that closed loop pole at -20. So what I'm going to do here is, I am interested in placing my closed loop pole at -20. So what I will do, so this is a very simple thing. Again, I'm writing x dot equal to minus x plus u. This is my system, but I want my closed loop pole to be at -20. So what I will do here, I will select, if I select u equal to x minus 20x, because control is in my hand. So if I select this something like this, then what will happen if I substitute this u here in my system, this one, then this will become x dot equal to minus 20 into x, and hence this is my desired specification.
Excuse me, sir. Sorry for interruption.
Yeah.
Sir, that v dot equals to minus x square plus x into u, right?
Sorry. This one.
Yes, sir.
X into x dot. But x dot is coming from here, right? X dot is, what is x dot? X dot is nothing. This x plus u.
Yes, sir. But when I multiply x with u, that I should get x into u there, right?
Oh, okay. So this x into u. You mean to say this is x into u?
Yes, sir. And u is
Yeah,
not
fine.
0.
No.
U is
If you assume u as 0, by default, by the definition, your system itself is stable. However, if you don't want to keep it 0, I will show you what to do with this one, how to use. But this is the case. Let us assume this is when u is 0. When u is non-zero, so okay, let me, yeah, this was a good point to, or v dot equal
Sir,
to
can you
minus
repeat from the starting, sir? Actually, because of the screen problem, I could not able to get what you are telling. Can you repeat the entire?
I will explain in a minute, sir. Let me come back to this particular point. So
Yes,
so
sir.
this is what we will be getting. So as Shivar Amar has told, v dot equal to, he found some typo in this one, that is very true. So v dot equal to minus x square plus ux. So what I will do here now, so since if u is 0, by default my system is negative definite. In cases when this u is not 0, then what I will assume is, I will be considering the case of negative semi-definite. So what by default, either I should make it less than equal to 0. I will show you the case when if it is equal to 0, what is going to happen. How do you select this u? So how do I select my u is, suppose for equal to 0, in the 0 place, u into x equal to 0. So x is the moving one. So I will take the x from here, u minus x equal to 0. Or if I select u equal to x, just let me see again, x square minus ux. If I select u equal to x, So this will ensure that V dot equal to 0. So if I select, there is some condition here. If I select some other cases based upon this one, if I want to ensure it negative definite, then accordingly I have to select this U. So if I select U equal to X, so this will boil down, so this will cancel. So this will make as V dot equal to 0. But that is not my intention. My intention is to make this V dot as negative definite. So what I will select, U equal to X minus X to the power of 4. Let us assume this. This is one such control law. If I use this control law here, then what is going to happen? This V dot equal to minus X square. This plus U into X plus X square will get cancelled. Okay. So again, this minus X4, X to the power of 4. So what this will do, these terms will get cancelled off. So eventually I am left over with minus X to the power of 4. So X to
No,
the
sir,
power
x
of
to
4.
the power of 5, sir.
Sorry.
X to the power of 5. X to the power of 5, sir.
Which one?
You select x cube.
It should be s to the power of 5.
Minus
Minus
select u minus u is equal to x minus x cube, it will be okay.
Okay. So this U into X minus X cube, because that is multiplied here X. Yeah. So that is fine.
Okay.
Yeah. So this is the way to select this one. However, if I want to, I want to replace this with the stable linear dynamics. You can able to see my screen, right?
Yes, sir.
Yeah. So if you able to, if you want the stable dynamics, what I will do is accordingly I will replace these terms. I will manipulate this controller such that it will become the linearized linear equations. I will show you one simple example here. The complete nonlinear equation. So this, my plant here is linear. You can see that the plant, whatever I have taken is linear. I will show you with a nonlinear plant how to do this one. I will take a very simple example of the nonlinear plant, and I will tell you how to derive this control law. Those who have missed this one, then if you can see this particular nonlinear derivation of the nonlinear control law, that will be, that will be quite, you can follow it easily. I'm considering my system as x dot equal to minus a into x square minus bx minus cx cube plus u. So this is my system where I will say that a equal to b equal to c equal to 1. So this is stable dynamics. So now, sir, somebody has switched on the video. Yeah. So now what I want my closed loop dynamics or closed loop dynamics to be x dot equal to minus 20 into x. This is the desired one. This is the desired dynamics. But however, you can see that there are lots of nonlinearities. I want to have this linear desired dynamics. So for this, what I will do here is, one way of doing this thing is simply if I select, because u is in my control, if I select u equal to ax square plus bx plus cx cube minus 20 into x. Okay. If I select this one, so now what I'm going to do, I'm going to use this here. So what that will do, x dot equal to minus ax square minus bx minus cx cube plus u, right? So this u is coming here, ax square plus bx plus cx cube minus 20 into x. So all these terms will get cancelled out, and eventually I am left over with x dot equal to minus 20 into x. So this is the fundamental
Sir,
theory.
sir, 1 minute. Sir,
Yeah.
why we need to cancel bx, sir? Bx is a linear
No.
itself.
Yeah. Please let me complete, sir. Please let me complete this lecture. Please let me complete this topic. Then we will discuss, sir. Then we will. So here, instead of the non-linearity, I cancelled the linearity as well. So this is one such way of doing the thing. I will tell you another way as well. So since one can always argue this B is there and this B is there, both are, the linearly, you can combine both of them. So you can use this B as well. But I am assuming that B also I'm cancelling. I will say that, due to some effects, I don't want to consider this B. Whether this B may be very large or so, then I can compensate this one. But I am assuming that everything, not only the linearities, I am considering the cancelling the non-linearity as well to bring this one. Okay. So the next thing here is the problem with this feedback linearization part is there might be some good non-linearities involved in this one. In these two things, there might be some good non-linearities as. How do we say which one is good and which one is bad? We are going to see now. So can you say which will exhibit a stable response? This x square and this x cube. Can anyone
X square.
Huh?
X square.
X square. Okay. X cube. Okay. So this we can see with a simple example, and we will discuss this one as well. So that's why this the Lyapunov theory comes into the we will use the Lyapunov theory to see which is the useful nonlinearities here. To start with our discussion, we will first of all we will see what is the useful nonlinearity here. As Amarendra has told, this bx, I can use this bs along with this one to reduce this particular value to 19 or so on, or to make it minus. So if this plus, then 21. If I make it 21, if this is 1, if I subtract this, then that will become that is 1. So now what I will show you here is what is the good linearity, good one and the bad one. So from our earlier example, what we have seen that if x dot equal to minus 20x or ax, this is quite a stable response. Now, so this is one control law. So where is this? This is one control law, which will give us minus 20 as the answer. I will show you another control law. So this is the feedback linearization. I'm cancelling all values, linear, non-linear. Generally in the feedback linearization, you cancel the non-linear thing. I cancelled the, in general, if this is a unstable one, let us assume, Amarendra Garu, let us assume if this B is unstable. That means
Yes,
instead of plus, if there is, if this particular is generating the unstable, then the good thing is you select the control law such that you should cancel this also, the complete dynamics.
Yes, sir.
And then you can
Then
replace.
it is the,
Yeah. So that depends upon the B value. So now what I will do is I will take another case. So I will say that this is the case number 1. That for the case number 1, my control law, I have taken ax square plus bx plus cx cube minus 20 into x. So this is case number 1. In another case, I will take u equal to ax square plus bx minus 20 into x. So this is my control law. So here the difference here is I have not considered this cx cube. So cx cube I am not using in my control law. What is my state equation? State equation is x dot equal to minus ax square minus bx minus cx cube plus u. This is my state equation. Now if I substitute this new case here, what it is going to become? It is going to become minus ax square minus bx minus cx cube plus ax square. I'm doing it right, yeah. The reverse way, okay. Plus ax square plus
bx plus
minus minus 20x. Okay. So now what is going to happen is these get cancelled. These get cancelled. So you are left over with minus c is equal to 1. So x cube minus 20 into x. So this is my control law. Okay. So now I want to see whether this is stable dynamics or not. Why? Because we have not cancelled completely. We want to see whether this x cube, whatever we are intentionally we have not cancelled, whether this x cube has some good properties or not. First of all, we have to see the stability of this particular system. This is already compensated system or the closed loop system, control activated system. We'll see the stability of the system. How do we see the stability of the system? Since there is only one variable, I will use x square. So that is nothing but x into x dot. So now what I will do here is x into x dot. X is the same thing. I will substitute the x dot from here. Minus x cube minus 20 into x. So what this will give us? This will give us minus x to the power of 4 minus 20 into x square. So this is, you can see that this is v dot. Okay. So v dot equal to minus x to the power of 4 minus 20 to the power of x square. So due to this particular fourth power and due to this second power, always it will ensure this v dot will be negative semi-definite, and hence my system is stable. So now the question comes here is, since I have not cancelled this nonlinearity, whereas in the earlier case I have cancelled the nonlinearity as well. If I have not cancelled this one, so what this will bring the added benefit. So this will bring the added benefit in the way that it will improve the damping. So it will make your system's response faster. How much faster it is going to make? Now you will see here. This you can find out unless you see my screen. I'm sharing the screen now. So this is the example. So this is my x dot has become minus c into x cube minus 20x. I assume that c equal to 1. In the screen, you can see that what is happening. Now I want to see really. So we have seen that by keeping minus x cube, so the system has some from the Lyapunov theory, we found out that it is negative definite. We can ensure that system is still negative definite. But the important thing to note here is that if you keep this x square, which is again in linearity, non-linearity, if you keep this x square here, then system will not, system will not follow this. The Lyapunov theory, Lyapunov stability cannot be, achieved. Why? Because if I take the derivative of that one, then it will not. Then you cannot ensure that v dot will be always be negative definite. But in this particular case, so that's why we had taken the x cube term. We have not considered the x square term. If we can consider the x square term as well here, we can retain that x square term, but we have not considered. If we take that one, then this v dot negative definiteness of this v dot will be, you cannot ensure that. So that's why. So what is the thing is, while designing just blindly, you can see that x square, like x term, x cube term, it should appearing here, and the derivative you are taking, if it is something x, then you have to choose, such that all things get cancelled and it should be replaced with this. Now what I'm going to show here is, I have done a very tiny simulation here. You can see the simulations file there. Can you able to see my screen?
Yes, sir.
Yes,
Okay.
sir.
Okay. So now you can see the same.
Sir,
Yeah. Hello. Yeah. Hello.
when we have the negative semi-definite, we need to verify the solution of the at a particular control value. We need to verify the solution also, no?
We say that the system is asymptotically stable, sir. For other stability,
Here,
we have to.
Here v dot we are getting as negative semi-definite.
Sir, what we will do is we will complete this this particular topic, and then I will give some time to the faculty to simulate this one. At the time, we can discuss, sir.
Yes, sir. Yes, sir.
Okay. So this is the simulation. So this is the simulation. What tiny simulation I have done. So this is the plant. The plant is, two inputs are going. One is x is going from here, and u. Two sets of controllers we have used. Two sets of controller. So this is x dot equal to plant of u of x, a equal to 1, b equal to 1, c equal to 1. And this is the same thing what we have seen. Minus plant is minus ax square minus bx minus x cube plus u. Okay, and this controller two control laws, I kept the two control laws. U1 is the cancelling out all these things, all terms, bx, cx cube, x square, everything I have cancelled, and eventually you'll be left over with x dot equal to minus 20x or so on. And another example what I consider here is u2 equal to ax square plus bx. So this term, so this I am not cancelling out this non-linearity. So what we will do is what I will do here is, so this is the response what I'm going to get. So you can see that the response of with control law, with control one, and without control one. So you can see that it is bit fast in terms of the rise time. So what I can say that the second control law is fast because we have not cancel out the non-linearities. So this is, so for the practical systems we should not always, so what is the lesson here is, for the practical systems we should not always cancel out the non-linearities by using the controller. There are two things. When you try to include more number of terms in the control law, so like this, if you include more, so obviously there will be a burden on, there is a computational complexity, there will be some burden on the computations as well. However, if you are retaining this one, there are two advantages. So the computationally complexity will be less, the first one, and the second one is it will have the additional damping. So this is what the fundamental philosophy of the backstepping. In the backstepping, we will not cancel the non-linearities. In the backstepping, not all non-linearities. We will only cancel the non-linearities which are not desirable or which are unstable or so on, and we'll retain the remaining all non-linearities, and then we'll design. So if it is a single state plant, what we have seen here, it is quite easy. You can see what we have done, and easily you can use this one. However, if the system has so many states, then you cannot directly use this whatever we have discussed in a direct fashion, because so that's where first of all you have to take one variable, then you have to transform it, and then you have to, from each step, it is a step-by-step process. Like backstepping is a step-by-step process, and then you have to calculate back to find the control action. So that is what the back stepping controller. So here what we have seen is that, so the lesson here is that if you are cancelling all the non-linearities, which is even desirable as well, your system might become sluggish, or or the computationally your system might be burdened as well. So the idea here is to retain the useful non-linearities, and cancel out and select the controller in such a way that it cancels all nuisance or undesirable non-linearities. So this is a tiny simulation. So what I will do is, I want to get the feel of this particular simulation. I'll be giving you another 15 minutes. In 15 minutes, please do this one. I'll be sharing you the slides as well. 10 minutes, it's 10 to 15 minutes. It is around 7. Let's see, what is the time now? It is around 7:24. So we will meet at 7:35 or 7:40, and then we will start the backstepping. I will sending you the slides. Please do this simulation and try to get the feel of the purpose, and try to change the C values as well. C values I kept as one. You can change the C value to 10 and see what is happening. Is your response is getting converged fast or not? So this is what I want to do you. So please take 10 to 15 minutes of time, and then we'll meet. Amrendra Garu, we can have the discussion once this session is over. So others during the interaction session. So please, all of you, please do this tiny simulations. What you have to do is this a plant, the same thing, the control, same thing, two different control laws, and this is a switch, and you try to play around with this C term. By default, I have used the CS1 and so on, and try to see what is happening if you use these two terms, and the C is in my control. I can keep any of the values, whereas here I have cancelled out and I have replaced it with minus 20x. But you just play around with different structures of this controller and see what is happening. And one such simulation you can always do as, you select U1 instead of removing this cx cube, keep the cx cube here and remove this ax square and see what is happening. If you're removing the ax square from this control part, so that means it is not getting some of the terms minus ax square will not get cancelled, and you can see what is happening here. So I will give you 10 minutes of time, and then just I will quickly, I will send you the slides now, the complete slides in a minute, and then we will see how to proceed further with the backstepping. I'll be sharing you this. Okay, I just shared you that file. You please see. Just take the 10 minutes of time, and then we'll see the backstepping approach.
Hello, sir. Hello, sir. Hello,
Yeah, hello. Hello.
sir. Sir, we have to design the Simulink model, sir. For that
Sorry.
one, Simulink model we have to design, sir.
Yeah, of course, sir. Of course. It is a small thing itself because everything is given. I have sent you the slides as well.
Okay, sir. Okay, thank you. Sir.
Yeah.
Hello, sir.
Yeah. Hello.
Hello.
Yeah.
From
Hello.
where we can get the states, sir? States block.
Which things the states block?
From where we can get it?
The state that is to workspace. You go to the out sinks. In the sinks, it will be there to workspace.
Things, sir.
Then just to see the results, it is not required, sir. You can go to the sink sink.
Oh, okay, sir.
In the two workspace, it will
Sir,
be there.
okay, sir. Switch, sir. FPST, sir.
To workspace. To workspace.
Okay, sir.
Okay, so we will start our discussion on the backstepping controller. Please go through this, whatever we are discussing now. This is very important, and follow as much as possible. So we will start our discussion with a backstepping nonlinear system, which is a second order nonlinear system, which I will assume as already I have sent you the slides if you want to see what is that. So this is the second order nonlinear system where this f of x is any nonlinear term where x2 dot equal to u and my output y is x1. So my objective is y to go to 0 as t tends to infinity or asymptotically stable. Asymptotically it should go to 0. Sorry, y should go to 0 as t tends to infinity. So this is my purpose. So y is the output. So basically this backstepping is a two-step procedure for this particular problem. I will show you what to do. The first thing here is you should, in one domain, in this domain, x1 and x2 transpose. That means x1, x2 vector. So the transferred coordinates, I will say it is a phi of x, some transformation. What is this? I will tell you. And I will say that z1 and z2 are the variables. z1 and z2 are the variables in the transform domain. So why this transformation is required and other things we will see now. So this is what we are interested. X equal to, our aim is to y of t should go to 0 as t tends to infinity. This is very important. You can see that this f of x1 is non-linear one. So basically this is a two-step procedure. Two-step procedure. So the first step is, first of all, we have to consider, since first variable, how to consider the first variable. Since we want the y to go to 0, we'll select as z1 equal to y equal to x1. So this is my first variable z1, which is nothing but the output of the system, which is nothing but the x1. This x1 I wanted to drive it to 0. So that is my thing. So now what I do is I will assume it as virtual control. I will consider the virtual control as my x2 equal to alpha 1 plus z2. What do you mean by the virtual control? That means here, if you see, if you consider only one particular state, if you consider only this particular state, then virtual control means, if let us assume this v. So if it is only one state, if this is my state equation which is only dependent on x, the another parameter I will consider it as a virtual control v, and this is again x2 equal to alpha 1 plus z2, and this z2 is the second variable. So this is, the procedure is more or less the same for all such backstepping control design. So now what I am interested here is, I am interested in taking the derivative because I want the dynamics. I have two transform state z1 and z2, but I am interested in the dynamics z1 dot. So z1 dot, I will get it. So z1 dot is nothing but my x1 dot. So this is from here you can see that.
Sir, excuse me, sir.
Yes.
Sir, your screen got struck. I am not able to view anything on the screen.
Others can see my screen.
Yes, sir. We can see you.
Yes, it is clear.
Madam, it is a problem from your side, could be.
On mobile we can see, sir. System we cannot see. We cannot.
Hello, sir.
On mobile we could able to see, sir.
I think it is the individual problem.
You can click the view camera, view active cameras. You can see, sir.
View active cameras, yeah. In the top there will be view active cameras. You can see. I can see in my desktop the same thing what I'm writing. So I think it is visible, sir.
Hello, sir. Could you please repeat?
Okay, sir. I'll just check it out. Sir, please continue. I'll check it out, sir.
Okay. So now what I'll be doing here is, I'm interested in the derivative of this transform dynamics. So what I will do here is z1 dot, since my z1 and x1 are the same, so whatever this x1 dot here is there, instead of x1 I will write it x1 dot will become z1 dot and this x1 will become z1. So now So now this Z1, if I substitute that one plus this X2, since X2 is there, plus X2 term will be there. X2 is nothing but alpha 1 plus Z2. Okay, so this is my first equation. This is my derivative of the first equation. But now what I'm interested in, I'm
Hello, sir.
interested in,
Hello, sir.
yeah,
Could you please
yes,
repeat
Ashwini.
once? Could
What,
you please
which
repeat
things,
once?
which one you want me to repeat? From where you want me to repeat?
Kindly
Ashwini?
repeat this what you have written now.
Okay. I will repeat it. Okay. All of you, please listen carefully. I'm not going to repeat it again. Please see this x1 dot equal to this is f of x1 plus x2. So this is my system of interest, where this f of x1 is the nonlinear term, and it is a second order system. The x1 dot is given by this, and x2 dot is given by u. And y is my output. Output is my first state, and my desirable, the desired thing is desired specification is I want my y2 to go to 0 as t tends to infinity. So this is an asymptotically stable condition. Asymptotically, it should go to 0. That means when t tends to 0, y of t should go to 0. So this x, my state vector, my Planck vector has two states, x1 and x2. And this z, I am doing some coordinate transformation. And the two state variables in the changed coordinates are z1 and z2. So I assume that z1 equal to y equal to x1. So the variable which I want to control directly is I have assumed as z1, which is nothing but output equal to x1. So x2 I have assumed that. So this is basically I assume that this is generally, now if you consider only the first equation, only the first step, this we can consider as this, we can call it as a virtual control, because it is something like x dot equal to ax plus bu in the standard linear form. So x term is there plus bu term. So if this x2 is not there, if it is only scalar, x dot equal to f of x plus x, some u term. So this is called as a virtual control law. So that means whatever the terms which are different from this particular x1 state, we can combine them and we can call it as a virtual control. So in this particular case, x2. So how I have selected the x2 as x2 equal to alpha 1 plus z2. So this is what I have selected, and this z2 is my second backstepping variable, this z2, and x2 equal to alpha plus z2. We will see what is this alpha. We'll see in the coming in few minutes. So this I am interested in the derivative of z1 dot and z2 dot, because then only the new coordinates I can able to define what is happening. So this z1 dot is nothing but this x1 dot. So in terms of the z, f of z1. So earlier it was f of x1 because my x1 and z1 are the same, plus x2. If you see, x1 dot equal to f of x1 plus x2. Okay. So now this, since my x1 and z1 are the same, so I have replaced this one here. So this x I have replaced with z1. So x1 dot has become z1 dot, and f of x1 has become f of z1 plus alpha 1 plus x2, because this is the x2. I assumed as alpha 1 plus z2. So the same thing is appearing here. Now what I will see is, as a first step, in the backstepping controller, we will keep on doing the design for each variable, each transformed variable, until we go to the next part. So before going to the before going to the further discussion, one very important concept which is called as a relative degree, which is called as relative degree. So until when we have to go till doing this, feedback linearization or the backstepping control, that tells upon the relative degree. The relative degree says that number of times you differentiate the output so that input appears. Listen very carefully. I will show you what is the relative degree of our system. The number of times you differentiate my output such that input appears. So first of all, we'll see what is the relative degree of our system. x1 dot equal to f of x1 plus x2, and x2 dot equal to u. This is my system, and my y equal to x1. So in this thing, it is not appear directly. So what I will do, y dot equal to x1 dot that equal to f of x1 comma x2. There is no control term here. F of x1 comma x2. So x1 is there and x2. I just combine together. Again, if I differentiate y again, so what is going to happen? Since x1 dot equal to x2, x1 dot equal to x2, so this will become x2 dot. Okay. In the x2 dot, the u terms is coming. So 2 times I differentiated the output such that this input appeared. And hence I will say that the relative degree of my system is 2. So this is very much important, this concept of relative degree. Okay. So now if we continue our earlier discussion, if we start with our earlier discussion, so we have seen that what is z1 dot? Z1 dot equal to f of z1 plus alpha 1 plus z2. This is what we have already seen. Now we will go for the Lyapunov function CLP. What I will say that v1 equal to half into z1 square. v1 equal to half into z1 square. This is the positive definite Lyapunov function. Only I am considering for the first state itself. So if I take the derivative, this will become half into 2 into z into z1 dot. So this will get cancelled. So my v1 dot equal to z1 into z1 dot. And now what I will do is I will substitute this z1 and this is some different. So now what I will do here is I will substitute this z1 dot here and I will see what is happening. So this will give us z1 of f of z1 plus alpha 1 plus z1 into z2. Because z2 then again we are not doing the same mistake what we did at so z1 into z2. So it is appearing like this. Now so this is my Lyapunov function CLF. So now how to select this alpha 1? We will discuss about this term later. We'll discuss about this term later. But how to select this alpha 1 to make this complete system stable? So the idea is we have to select an appropriate value of alpha 1 such that my closed loop dynamics v dot will be negative definite or stable. So what I will select is alpha 1 equal to f minus f of z1 because I want to cancel this effect of this function minus k1 into z1. So if you substitute this in this particular term, then my v1 dot will become z1 into this term will get cancelled. So minus k1 into z1 plus z1 into z2. Okay. If I further write, this will become minus k1 into z1 square plus z1 into z2. Okay. I think this is clear. Minus k1 into z1 square plus z1 into z2. So now my system, my v dot, v1 dot for the negative definiteness, if I assume, I cannot assume z1 as 0 because z1 if I substitute z1 as 0, then everything will become 0. But which I don't want because that is a state which I'm considering and it want to be changed with respect to the time. If I consider z2 equal to 0 for this particular thing, if I assume that z2 equal to 0, then my z1 is stable because if we trace it back, so z1 is stable. So what is my control dynamics here? The control dynamics, if I choose an appropriate value of alpha 1 like this, then it is going to give me the stable dynamics. But now I will see that why this alpha value is required, because if you remember x2 equal to, from our definition, x2 equal to alpha 1 plus z2. So now we are slowly coming up the alpha 1 or the second state in terms of the first state, because that is what we want. So alpha 1, if I select this alpha 1 as this value, then my first state is stable. So that's what I can see from here. Okay. So next step, what we will see here is we will use slowly we will increase the complexity. So now we substitute the same thing here, this alpha 1 in this Z1 equation, wherever this alpha 1, then my Z1 will look like then that will make us my Z1 dot. If you remember, so if I substitute the same thing, my Z1 will become minus K1 into Z1 plus Z2. So this is my now, this is the dynamics. And now this dynamics, you can see that it is only in terms of Z1 and Z2, no other parameters. Whereas in the earlier expression of Z1, what we have seen earlier, so earlier was Z1 dot equal to f of Z1 . Okay, and since if I substitute this alpha 1 and it will get cancelled and eventually you are left over with this one, but this anyhow this Z2 is there, so that's what this Z2 is. So this is my first dynamical equation. This is error dynamical equation. Next, what I want to here is now I'm interested in Z2. So this I will say it is a one equation number 1. Okay. So now what I'm interested here is, so since this is already known to us, so I will just sorry, somebody was calling, so I have to disconnect it. So now I'm interested in Z2. If you see our equation for Z2 equal to x2 minus alpha 1. So this is what in the very first stage we have considered, that x2 equal to, in the other way, if you send to the x2 here and if you bring this alpha here, x2 equal to Z2 plus alpha 1. That is what we have assumed it earlier. So now what I'm interested here is I will take the derivatives on the both the side. This will become Z2 dot equal to x2 dot minus alpha 1 into dot. So we have derived the expression for alpha 1 dot earlier, and if you see from our plant dynamics, this x2 is nothing but u, so that will become u minus alpha 1 into dot. So Z2 dot equal to u minus alpha 1 into dot. You know what is this alpha 1 other? So now we are interested in the stability of Z2 as well. So how to derive that one is, first of all, I will consider the closed loop Lyapunov function as v2 equal to v1. V1 already we have done, we have discussed. Now v1 is related to the first Z1. So now we are interested for the second one, Z2 square. So now what is going to happen if I take the derivative? If I take the derivative d by dt, so this will become v1 dot, a 2 will get cancelled, so Z2 into Z2 dot. So now this v1 dot already we have derived earlier. So v1 dot we have derived and it is minus k1 into z1 square plus z1 z2. That's what we have derived earlier, plus z2 into z2 dot. Now what I'm going to do here is, here is my another color pen. Okay. So now what I'm going to do here is, this z2 I will substitute here. If I substitute this z2, z2 dot from there, so this will become minus k1 into z1 square plus z2 into, if I do certain manipulations and other things, so z1 plus z2 dot. I mean, just I rearranged this term first. I've taken the z2 common from here, so z1 plus z2 dot to make the things more, easy. So now I will substitute this z2 dot here, minus k1 z1 square plus z2 into, like I will leave this here, z1 plus u minus alpha 1 dot. So rather the same thing is this one. This particular terms is coming from z2 dot. So now, if you see this closed loop Lyapunov function, if you see this particular v derivative, v2 derivative, I want this to be the negative definite. So this term is already negative definite, provided this k1 is positive. So z1 square is there, so it is negative definite. Now I have to do something here such that my v2 dot should also be negative. So now this u is in my hand. If I select this u equal to, because it's plus minus alpha dot, I want to cancel the plus alpha dot. This z1 is there, so I want to cancel with minus z1. And since I want to ensure that z square term somehow it will appear, so what I will be doing here is minus k2 into z2. So now if I substitute this here, then what it will become? Minus k1 z1 square, minus k1 z1 square, exactly the same first term, plus z2 into, what is going to happen? This alpha 1 term minus alpha 1 dots terms will get cancelled. This z1, since positive negative, this will get cancelled. So eventually you are left over with minus k2 into z2. So if I write it further, this is the first time I'm using this manual thing, so things are getting a bit messed up. Yeah. So now what is my v2 dot? If I rearrange and write it, v2 dot equal to minus k1 z1 square minus k2 z2 square. And if you consider that k1 and k2 as positive values, or there are lots of other conditions as well. So this will ensure that v2 dot will be negative, except at z1 equal to 0 and z2 equal to 0. Except when z1 equal to 0 and z2 equal to 0, then my v of 2 will be 0. Apart from that, it will be always the v2 dot will be negative definite. So that's what I can say, that negative definite, except these 2 points. If you substitute this value, then my v2 dot will become negative semi-definite. Okay. So now the control law. So yeah. So okay, I forgot. So this is my control law from here. My control law, which is very much important, alpha 1 dot minus z1 minus k2 into z. So this is what exactly my control law. But however, there are two things here. My control law, whatever you are seeing here, is in the transformed coordinates. Okay, but you don't want to apply your control in the transformed coordinates. So what you have to do is you have to convert this into the real coordinates. That means in terms of the x1 and x2. And there is a derivative term here as well. So you generally don't want your control signal to have some kind of derivative terms. So how to handle this one is I will show you. So this alpha 1, if you remember alpha 1 equal to minus f of z1 minus k1 into z1. So this is what we have seen, and we know that z1 equal to x1 that equal to y. So this is the first backstepping variable. Now I want to take alpha 1 dot equal to, because this minus negative is there here, negative, I will take the partial derivative with respect to the x, because z1 I will substitute x into x1 dot minus k1 into z1 dot. So z1 equal to x1. So if I substitute, so this will become k1 into x1. Okay, this is my alpha dot. So this alpha dot need to be substituted here. This need to be substituted here. If you can see, this alpha 1 has the terms of only the x1 and x2. And you know what is z1? Z1 is nothing but x1, and z2 is also, you already have seen the corresponding expression for that one. So if you substitute my final control law, which is nothing but u equal to alpha 1 dot minus z1 minus k2 into z2. So this alpha dot I will take it from here because it is only this thing. Z1 is x1. K1 and K2 we have to find out what are they. and this Z2 is again we have to transform it back. How to do that one? I will just write this one. My final controller u equal to minus dou f by dou x1 of x1. Okay. I will write again this x1 dot is x2. You know this, what is this x1? This x1 dot equal to x2. And then if I rearrange this one, I'm directly writing the expression. You can rearrange on your own. Minus x1 minus k2 into x2 plus f of x1 plus k1 into x1. So this is my control law. So this is my final control law. The only thing is the partial derivative of the nonlinear function with respect to x1, it should be finite. It should be available. That is one such condition. Apart from that, this is my control law. If you use this control law, you can able to get the things what we have discussed. So this looks very complex, isn't it? This looks very complex, but this is what backstepping controller. So what I suggest you is, I have given you the slides already. You please do it by your hand, and this I have taken from the reference TTK 4190, which you can in the slides. So you go through this one for 10 minutes. So now it is 8:10. So go through this till 8:20. Then we will discuss the backstepping controller for DC motor, series DC, separately excited DC motor. The problem what we have discussed here is the output is going to 0. It is the regulator problem. It's not the tracking problem. For the tracking problem, what you have to ensure is the error dynamics. Instead of y going to 0, ey should go to 0. Ey means y minus y desired should go to 0. So if you want to go for the tracking problem, then that is what you have to consider. So what I will say that I have already sent you the slides. Please go through the slides and try to derive yourself. Now it is 8:10. We will meet at around 8:20 or 25, because this is very much important. If you don't go through it now, so it might be difficult at later stage. And if you have any difficulty or any fundamental understanding problem, this one we can discuss now itself. So another 8:10, 8:20 or 8:25 we'll discuss.
Excuse me, sir. Sir.
Yeah. Hello.
Hello, sir.
Yeah.
Sir,
Yeah.
can you please repeat that final control equation once? Can you? It is not clearly visible. The final control equation.
Final
that is,
control
I think,
equation.
minus 2fx. Yeah, minus
Okay.
2fx1.
Which one? This
That
is
one,
the actually this is the
last-
finite control law. This is the finite control final control law. So this is the same
last
thing. So
equation.
nothing.
Yeah, that is
So nothing to
last
worry about
equation.
this one. This one.
That is that equation. Yeah.
Yeah,
That
this one
equation.
I already sent in the
2fx1.
slides. You can see this one. So I will tell you how to get this one. This alpha one you can get it from directly from here. This Z1 is nothing but X1, and this Z2 we have already substituted alpha plus X2. This Z2 is I think alpha plus X2.
Alpha plus X.
Yeah. You just if you substitute, you will get this expression.
Okay.
Sir, this is Ravikran.
Yeah.
So how do we transform our plant into this form, sir?
Sorry.
How do we transform our plant into this form, like f of x1 plus x2? Like
there are various transformations are there. There are various linear transformations are there. So if you remember in the sliding mode control, if you see that it is called as a regular form. So that is called as a regular form. So regular form is one such form where you can transform your system into this particular form. You can go through regular. It is called as a regular form, or in some literature it is called as a feedback linearizable form as well. Or in some cases it is called as a chain form as well. Chain form, because x1 dot equal to x2, x2 dot equal to x3, x3 dot equal to x4. It will keep on in the chain form, whereas in the last state your control will appear. So that is a chain.
So we have to modify our plant into such that only in the last state you should be there.
It should be in the feedback linearizable form. Yeah, you have to transfer your system accordingly. In the last few states, it should be. You should make it the first few states independent of the control input.
So as many can we say that as many number of states, those many that much will be the relative degree of this plant?
No. The relative degree depends upon the number of times you differentiate the output so that input appears. Suppose if your output is in our case.
Okay, if the output is in x2 state 2, then only three
Yeah,
times only once is sufficient.
Let me write. Suppose x1 dot equal to x2. My battery is getting drained. Suppose u is appeared here, and let's say x1, x2 something. And if I say that y equal to x1 in general, okay, this is not in feedback indivisible form, but still the relative degree what you say that number of times you differentiate the output, the input should appear. So what I will do, y dot equal to x1. In the x1, there is this u term. So my relative degree is 1. So the relative degree of the system is 1.
But we cannot apply backstepping to this plant, right?
No, this you can you cannot apply. This you cannot apply.
Yes.
You have to transform the system. You have to transform the system by using various transformation. Yeah. Otherwise, what is the simple such thing is you transform z1 equal to x2 if you take, okay, and then this is one such thing. What I'm saying is I don't know whether it is exactly you can do it. Just I'm roughly saying, and you can say that what will happen z1 dot equal to x2 dot that equal to x1 x2 will come, and then you can take z2 as some other term so that the input will appear here. So you can see that in the first state there is no input. If I take z1 equal to x2.
Yes.
So this is one such very ad hoc way. I'm not saying that this is the exact way, but there are some standard ways to do that one. And the standard book for this one is Kokative by Peter Kokate, Nonlinear Control by, so whatever, Nonlinear Adaptive Control by Mirlo Kristik, Ionessi, and Peter Kokative. So I will write it here. Nonlinear and Adaptive Control by Kristik, by M. Kristik. I don't know, Ionis, I don't remember the spelling. Maybe the Ionis K, Ionis Kanopoulos, and Peter Kokative. And I think they are all, supervisor of, I think Kokative is a supervisor of Kristik and so on. So this is the thing. So this, in this textbook, if you follow exactly, this complete textbook, I think some 3-4 chapters have been dedicated to backstepping in the fundamentals. Though we have seen this only in very fundamental, very things, but if you want to have very detailed, so for the backstepping, you can go through this.
Okay. So for backstepping, we have to be like mostly it is an art, right? So how do we transform all these things?
It is not an art. I mean, you cannot say it is art. So that depends upon mathematical. Lot of mathematical intense equations will be there, which one should be aware of. Lot of transformations. Sometimes you have to use, several transformations to get this.
Even those transformations are not unique, no?
No,
we can have n
they are
number
not
of
unique.
transformations.
Yeah, infinite number of combinations are possible.
Yes.
Okay, so we will meet at 8:30,
Okay.
and we will discuss a paper on 8:30 or 8:35. We'll discuss a paper on backstepping for a DC motor application with the, it's not the output tracking, it is the state tracking. Thank you.
Sir, what is CLF, sir?
It is control Lyapunov function. Control Lyapunov function.
Okay. Thank you.
Sir, I'm Ravi Kumar speaking.
Yeah, Ravi.
Sir, if we have more number of state variables in a given system, then so many steps will be having, sir, in this backstepping algorithm.
Yes. Yes, it doesn't depend. If you can convert into the chain form, only all other things are the standard except the last few states.
Okay. So there is no hard and fast rule that we'll be having. If we have 5 states and we'll be having 5 steps in the. Depends on how we manipulate.
Yeah, it is completely based upon how how is your transform system looks like. In general, your transform systems and your actual system should be of the same order.
Okay. Okay.
Hello, sir.
Yeah, hello.
Sir, if my initial system itself is unstable,
Yeah.
Then there is no point of transformation, right?
Initial system is unstable. Why?
Sir, actually, you have taken some system to check the
Yeah.
and you are assessing the stability through your Labne functions.
Yeah.
And this Labne function helps you in controlling also.
Sorry.
And the same Labne functions can be used for the controlling also. So my question is,
Yeah.
and I have
Yeah.
suppose my system is deliberately unstable. Assume that. So can I make it stable?
Yeah, that is the purpose of the controller design. You have to select in a such a way that if there are unstable poles, unstable things, that you can cancel out and you can replace the desired one. In our case, we can say that f dot equal to something is there, right? F of x plus some terms. I don't remember. You can consider it as a, some positive value instead of the negative value. Or f of x, you can take it as x1 square, and you can derive the same thing. Then obviously it will be, it should stabilize. So that is the purpose of
Okay.
that.
And
whole,
one more thing. Yes, sir, I got it. And one more thing. Here you have taken two Leibniz functions separately. So why can't I take
that
z1 square plus z2 square by 2?
no. That is actually the philosophy of backstepping. You have to do one at a time, and then you have to go to the next. If you cannot use the complete, it will not. You can get it, but it is not the backstepping. In the backstepping, you have to first of all one you have to do, and you have to ensure that that one is stable, and then the next one you have to go and you have to make it stable. So that is the process of backstepping. If you're considering complete thing, then it will be completely messed up. Then that is not called as a backstepping approach.
Okay.
If you see in the sliding mode control or something, we consider half, all states the Lyapunov. So this is not the backstepping. In each state, we ensure that it is stable, and then we'll proceed to the next state to see the stability. In another 2 minutes, we'll start our session.
Parni sir. Parni sir. Parni sir. Parni sir. Parni sir. Can you hear me? Sir, can you hear me?
Yeah, okay. So we will start our discussion now on the paper. Am I audible? Hello?
Yes, sir.
Yes, sir. Okay, okay, fine. So we will discuss the paper. Let me open that paper. Yeah, I'm sharing this my screen to you. Yeah. So this is the paper what we will discuss today. So the paper is the backstepping control
Hello,
of
sir.
a separately. Can you able to hear me? Somebody from Krishna Jyoti? Any issue? Okay. So we are going to discuss the backstepping control of a separately excited DC motor. And this was published in Electrical Engineering Journal in 2018. This journal is not of that top quality what we discussed in the previous days. So we had discussed IEEE and so on. So the quality wise, this journal is of not that quality. So there are 4 authors. It was submitted in November 16 and June. So around 8 months it took to get accepted, and immediately got published in 2017. Though this issue number, what you can see that, and the other details are 2018. So they have considered DC motor. I will not go into details of all these things. Everything you can go through. This is the straightforward DC motor. And here they have used 2 different controllers. One for the position control, and another one is the speed control. So they have compared their speed control and position control. They have compared the response with PI controller as well. So I will not go into these details, which is very trivial. So this is what they have done. The very simple thing. The thing which is of our interest is the speed control, backstepping control technique. So in the speed control, what we have to do here is we should ensure that the actual speed is going to the reference speed. So that's what they have considered. So my here aim, unlike the earlier one, the output should go to 0. But here, instead of the output, the error, because here I am interested in the tracking one. Instead of the output, I want the output error. So the error between the reference speed and the actual speed should go to 0. So that is what happening here. So that is what step 1 I have selected the E1 as omega r minus omega r star minus omega r. So this is the reference. So this is how I have taken the derivative. E1 dot equal to omega r minus omega r star minus omega r dot. So again, similar to us, what we discussed, they have taken the first state variable v1 equal to half into e1 square. Half of it get cancelled to take the derivative, and this becomes e1 into e1 derivative. So e1 dot is this expression, which is nothing but omega dot into star minus omega dot. So this is the omega dot expression. And now the purpose here is how to get this one. And this is the manipulating this particular equation such a way that this v1 dot will become the negative definite. So very simple way what you can do is v1 equal to 0, and then you derive it and then add some negative definite term, so that you make this particular as the negative definite. So this is what. So that the reference current IA star is chosen as. So from this Lyapunov derivative, you should ensure that it should be negative definite. From that, how to ensure that one, this IA is in your control. This IA you have obtained like this. In the next step, what they have considered is EA E2 equal to IA star minus IA. So E2 dot is IA dot minus IA. So again the derivative. And interestingly, IA star you have obtained from here, and then we'll be doing further analysis. This is very much similar to the one what we have seen, half V2 equal to V1. We have seen V1 plus this thing. So V1 is nothing but half E1 square. So here you can see that V2 dot equal to E1 E dot plus V2 into E dot. So this is this we have obtained from earlier one. And if I rearrange, if I substitute the corresponding E1 dot and E2 dot, whatever I have got, I'll be getting like this. So eventually I am interested in this VA. This should be the capital VA or VA star, and then I will rearrange this in such a way that this V2 dot will always be negative definite. So that is the way what they have done here. So and then they have done the simulations. This is what actually you want, and they have seen the responses for various steps and other things. All the parameters are given in the table 1 of this paper. You can go through that one. So this is basically for the speed control. For the position control, if you see, they have considered this particular theta dot omega dot, and the C is the torque. They have represented torque with CE. So this is my plan. So we'll see how to proceed further. So again, since here, if you see here, since my aim is the position control instead of the omega control, angular frequency, this is the theta dot. So theta is, I want the theta to track the reference. So that's why I have taken E1 equal to theta. This is the this is the theta, and the earlier one was the omega. So E1 dot I have done like this. So theta dot equal to omega r, which is from our equations, and theta dot star are the same. So again we have done the same thing, half E1 square, which is nothing but E1 into E dot, and then we have derived the derivatives, and we have substituted. We have found out this omega r star, and we have rearranged in such a way that eventually v1 dot equal to minus k1 into E1 square will only be there. So this part we are making it as 0 by suitable selection of omega r star and so on. So only this negative definite v1 dot is there here. In the next step, what we will consider is E2 equal to omega r minus omega r star, and omega r star we obtained from here. You can see how it is happening step by step, because it is taking the values from the previous one. And what I'm interested in E2 dot. E2 dot again, I could able to get from this equation E2 dot equal to omega r dot plus k1 t1 dot minus theta 1 dot double dot and so on. So theta 1 double dot is coming here. And then again, why this E2 dot is required? Because E2 dot is required to calculate this particular problem. So this particular parameter here, V2 equal to half into E1 square plus half into E2 square. This is my Lyapunov function, and the derivative is like this. So all other values are available with us, E1 dot from the earlier one and E2 dot from here. Then my aim is to ensure that V2 dot should be negative definite. So then accordingly, I will rearrange my control law, and I will derive my control law, and V3 is also there, the third variable. So because it is a third state, V3 is basic. I think this C is the torque. So again, C minus C star and E3 dot, and the C3 dot. The process is very much same. V3 you can take half into E3 square. This is a separate entity. So that's why they have not added the affiliate to omega and theta. So they have separately designed for this one. VA dot, how it is coming, and all other parameters. E3 into E3 dot, and then E3 from this you can take the derivative. E3 dot is given here, and you substitute, and you have to ensure that V3 dot is also negative definite, and accordingly you have to select the VA star. So this is your final VA star, and they have done the simulation with these backstepping controller, and they have verified the performance here as well. So until this, you can see what is happening. And this is adaptive backstepping control technique, which we have not discussed here. If somebody is interested, they can go through this one as well. But we have discussed only this part. So this is today's topic, and this is the corresponding paper what you can you want to simulate. Everything is the same what we have discussed, only the plant has changed and the control has changed. So eventually finally you want to simulate this. So this is my final control of VA star, and you just, this is my, I think the reference of VA star is the voltage. You can substitute and you can able to get the corresponding backstepping controller. So that is what from my side. I will just in a minute, just give me a break of 1 minute. I will send you the quiz link, and then we can have the discussion for 10 to 15 minutes. Just give me a minute.
Sir,
Just give me a minute. Just give me a minute.
okay.
Oh, so many things. Just give me a minute. Let me type the. Already the details of this paper I have already sent in the afternoon, that we are going to discuss this paper. So you can go through that one. Yeah, already I have activated this FDP. So now we can discuss. Yeah, madam, someone was talking. Hello, somebody wants to have some clarification.
Yes, sir. Actually,
Yeah.
hello, sir.
Yeah, please tell.
Actually, I'm from control background. I can work with,
You are,
I know how to deal with SMC, sir. But coming to backstripping, I can do only the theoretical calculation, because the theoretical calculations I understood previously and I did it, I gone through it. But the problem is I don't know how to start the simulation for backstripping, sir. From your explanation, what I understood is we have to make the same
yeah.
plant block. Instead of taking a controller line like you can see controller block, we are going to calculate the whole paperwork. Finally, only the controller, we have to use it as a U value. Or is there any different type
No,
of
that's
simulations
what.
we can use?
No, that is the same. That is the same. If you see the first simulation what we did, in somehow it is the backstepping controller only. The first simulation, the toy problem what we have
Or
seen,
if you have
SBL
any,
one we have used. Sorry.
yes, sir. Yes, what my request is, if you have any backstepping controller part you did, just show us that how.
No, the same paper what I
Just show
showed
us,
now.
no
You
need
just
to
replace the. No, I just showed you that thing, right?
control.
That control part. Just substitute that controller. The first problem what we have simulated, it is the same. There are two controls. One is feedback inversion control, and the second one is inherently that is a backstepping control. Without explaining the backstepping control, we have that minus E1 cube something we kept it, right. We haven't cancelled. So that is a final controller what you're interested. That's what you want to implement. Nothing more than that. All the theoretical calculation is just to calculate that controller.
But if the system is a huge non-linear system, how if
Then your
are we
controller
can
will
get
also be very
finally
huge.
the control law?
Yeah.
Sir,
Yes.
sir. But are we can get a
Yeah.
control law with actual system states or transform states? Are we can change the transform states into actual states? Sir?
No, you have to transform back the transform states. You have to transform back your transformed states to the actual, real states. Your controller should not be based upon the transformed variables. You have to transform it back to the actual variables. So that's what we have seen x1 and x2. How you have brought it into x1 and x2, not the controller in z1 and z2.
Yes, sir. Yes, sir. That only my doubt, sir. Is every problem is possible to convert or not? I'll try, sir. Thank you, sir.
Yeah. How to choose the values of K1, K2 for backstepping control. So basically, that is actually, if you, that depends upon what I have just shown you the linear control format, minus k1 into k2, minus k1 into kind of z1 minus k2 into z2. So that you can use any state feedback control. Either you can use the pole placement, you can use the LQR controller, or even you can use the HNPT controller as well as full state feedback control. So that depends upon where you want to place your poles, how fast you need the convergence, that k1 and k2. Anything else? So tomorrow will be the last day. So I request you, all of you to be there without, what I mean to say that without fail. So I don't mind if you have not attended the first 5 sessions. Tomorrow is very important session. I request or may I make the mandate. All of you should please, all of you please attend this one. So tomorrow session will not be too long. I will start sharply at 6:30. And by I will wind up my actual session by 8 o'clock. And 8 o'clock there will be some validatory and small feedback session for 10 to 15 minutes. After that, immediately I will give you the quiz. As soon as this validatory is over, so immediately I will give you the quiz. And from then, 30 minutes time will be given. And I'm very strict about this one. I will lock. I will lock completely. I will lock completely. I will not keep the link open. So as soon as the validatory is over, if it is over by 8:05, then I will start at 8:05, and 8:35 I will lock it. So my sincere request is all of you please attend tomorrow's session, which is 6:30 to probably 8 or so. Mm. And what I'm saying that I am trying to host one SDP for the students. So it will be in the similar way, but it will be not this much intensive. So student development program for the next week onwards. If any of your students really want to learn hands-on practice, have some hands-on things, then please let them ask to register. Tomorrow I will send you the flyer. If you really think that if you have benefited this from this FDP, and if you want your students to get benefited from the SDP, student development program, then they can attend. The fee I kept very nominal, 100 rupees. That is also just to avoid the unnecessary students. So just simply, if that is the current trend, if they see that something is happening, people will simply jump into that one and they will not participate. So really, if somebody is really interested to participate, or want to have some hands-on control system designs using the MATLAB, please pass on this information to them. Tomorrow I will spare you. It is after a couple of weeks, I think. So July 2nd or third week, I think we are planning that one.
Sir?
Sir.
Yeah.
Hello.
I am Dr. Naik.
Yeah.
This is Sharat.
Yeah. Please. Yeah.
Hello.
Actually,
So what
for
is
the
the
students
fee,
who
sir?
are
What is the nominal fee?
Or the
100
next week.
rupees is the nominal fee for the students. Even faculty can
Fine.
also attend.
Okay, sir.
It is 100 rupees
Not
only.
Fine, sir.
Just I don't want to charge students, burden the students. We kept it 100 rupees.
Sir, charge is not a
for 1
matter,
week.
but the topic is the same topic.
No, sir. It matters because it matters to the students, sir. Maybe it may not matter to us because there are many. And further, if students are really very interested and they have the financial condition, I can give the fee waivers. I given the 10% of this FDP as well to the fee waivers to the faculty as well. So they have to tell me the personally the reason. Then that can also be waived.
Yeah. Thank
That
you.
can also be waived off. Yeah.
All right. Thank you.
Hello.
Yeah. Hello.
Sir.
Yeah.
Sir,
Hi,
good
Murli.
evening, sir.
Good
Yes,
evening.
sir.
Good evening.
Sir, regarding this SDP, I mean student development program you have said, no, sir. So the basic prerequisite for them is the UG control system course. Is it enough, no, sir?
Even if they don't know also, they can attend it. 75% of the course they can follow up. 25% they cannot able to follow if they have not done the undergraduate control systems. 75% they can
Okay.
follow up.
Okay. So I
I will
asked
again
this question
record the
because
videos
the theory,
hands-on.
Yes.
Yeah.
Sir. Yes, sir. Okay,
Anyone
sir.
can
Thank you,
attend,
sir.
but if they have not studied the control system, 75% they can follow. The 25% they cannot.
Okay, sir. Okay, sir. Okay.
75. Yeah.
Okay, sir. Okay. Okay. Thank you, sir. Thank you.
Yeah.
Hello, sir.
Yeah. Hello.
Sir, if permits, can you
Yeah.
explain proposed stability criteria also?
Yes, please.
No,
Banu.
if time permits, can you explain proposed stability criteria, sir?
That is beyond the scope of this. I mean,
Workshop.
it may be of your personal interest, but before explaining the Popo criteria, I have to explain, the linear stability, non-linear stability, and there are lots of mathematical things are involved in this one. So I don't think the faculty will, appreciate that one. They should be
Anyone
aware of
reference for
Nyquist
me?
plots. It need to, we have to explain the Nyquist plot, Nyquist stability theory, and then going to the Popo will be the good thing. Yeah.
Sir, any one reference that you can suggest for that?
Yeah. Hello.
Sir,
Hello.
any one reference for that, sir?
I think Slotin and Lee, nonlinear control, Slotin and Lee, they have discussed. And Khalil has also, I think, Hassan Khalil, nonlinear systems, they have discussed. That's what I remember vaguely a long time back. I have followed these two books for that one.
If
So which one is
sir, if I could add to his question, there is actually I think you have a NPTEL course by Professor M. Madhu and Belur from IIT Bombay. You have a complete description of entire Popo criteria, all the nonlinear system analysis. Even you can refer the recent course of IIT Madras by Professor Ramakrishna Pasmurthy and Arun Mahindrakar.
Yeah, you can follow.
Thank you.
Sir, this is Satya from IIT Bhubaneswar. I have a small question, not exactly to backstepping, but I just have a doubt. Like, can we say that adaptive control and or can we say that fault tolerant control is a branch of adaptive control?
If you say it is not exactly, because the plant parameters, you are not, whatever, if you see the fault tolerant, at least the fault estimation what we have did, we have not changed any parameter with respect to the fault. So it is not varying. So it is only the constant parameters itself. So similar in the fault tolerant control as well, we will expect the constant parameters to handle the faults. However, if those parameters are varying with respect to time, then that is called as an adaptive fault tolerant control. And in general, for the practical systems, preferring this adaptive fault tolerant mechanism is not the suggestible one, because it need a very huge computational, and computational complexity is very high, and that's not the industry actually wants to use that one. Else, if they really wanted that, they can go for that one. So the fault tolerant control, I mean, which I have not discussed here, based upon the redundant actuators and the redundancy of the system, one can always design that one. If you want, I can send one of my papers which I have published in fault tolerant control. But this fault tolerant control is not exactly the adaptive control, but you can treat the fault tolerant control as adaptive if the parameters of the fault tolerant controller are varying with respect to faults, or with respect to any change in parameters.
Sir, or can we say like adaptive control is only concerned with the changes of the plant, like, but whereas
Sorry.
fault tolerant control, yeah, control is concerned with the changes of the plant parameters, uh, or is it like
You
control involves many
sorry,
the
your voice is breaking. Satya, your voice is breaking. Your voice is breaking.
Excuse me, sir.
Your voice is breaking.
Excuse me, sir. This is
Yeah.
Nedumalpugal.
Yes.
Yeah, sir.
Yeah.
Can we apply these type of controllers for chemical plants, sir, which is having high nonlinearities?
Yes, you can apply. Why not? Why not?
Okay.
There is no
Because
such restriction that you cannot apply to these things. You are always welcome to
the
apply.
plants having larger delay and all, we can go for it, sir.
Yeah, you can apply. But however, specifically, we have not we have not designed. Inherently, it can handle the time delay in the sensors, the information which is coming out the sensors or so. But we are not specifically designing the time delay control. There are another, sect of controllers which can directly handle with this time delay. And there is some theorems. There are some theorems as well which will tell you that up to what before implementing the controller itself, you can tell the closed loop system up to what time delay it can able to tolerate. Your control system can tolerate some based upon certain mathematical theorems. So that is that. But as such, we are not discussing the time delay, but inherently it will take, some of the controllers will take care inherently.
But most of the literatures they are focusing towards only that predictive controllers are like model predictive controllers for the
MPC. Yes.
Yeah,
Yeah,
they're not
but you can
coming for
apply it.
these.
There is no. Yeah, because it is
So
bit
we can explore.
the mathematically challenging one. Maybe in the future I will cover this MPC and H infinity and other things if time permits. Maybe after a couple of months or so, based upon my availability. But
So still this
that is
area has
different
been
class
open
of
for the application of these
that
type
you
of
have to see.
controllers for the plants.
That
You
you
have to
have
see
to
the
see, sir,
literature.
in your research area whether it has been applied or not. Yeah.
Okay, sir. Okay. Thank you very much.
Yeah.
Sir, this is Satya. Sorry for the disturbance.
Yeah.
So what I was saying is that can we say, is it like the general idea of adaptive control? What we know is that handling the changing parameters of the plant, whereas fault tolerant control in general will include many things other than the plant parameters only. Is it like that?
See, if your faults are affecting the parameters of the plant as well, if your faults are affecting the parameters of the plant as well, then you can say that it is an adaptive one. But as such, in general, if you say the normal in its naive form, fault tolerant control, it does not assume, it does not explicitly consider the change in parametric variation, whereas there are adaptive fault controls as well, so which will work not only when your plant parameters are constant, when your plant parameters are varying as well, then it has the capability to deal that situation. So these are two different two different branches of the control system where people have combined both of them as well, but in general they are treated as generally separate entities. However, adaptive fault tolerant control mechanisms are also there, which have the capability to deal with change in plant parameters as well.
Okay, got it.
Yeah. Okay, so I'm ending my session here. So tomorrow
Sir,
we'll meet at sharp
one last
6:30.
question, sir.
Yeah, Ravi.
In the quiz you have asked for relative degree, no, sir? You gave only the plant parameters.
That we'll discuss over offline.
Okay.
Yeah.
Sir, can I ask one question, sir?
Yes, sir.
Hello.
Yeah, please, sir. Please.
Actually, he
what is the what is the characteristic difference between the sliding mode, backstepping, and backstepping conventional?
Sliding mode, backstepping,
and backstep. So whatever the backstepping we have used or discussed today,
So
is
so
it
yeah, in its naive form, sliding mode control has the capability to reject the uncertainties or disturbances of a certain class. But here
so
we are
here
not in the
whatever
backstepping. Yeah, please, sir, let me complete.
whatever
Here, whereas in the
whatever, sir, can I ask one small thing?
please. Yeah, please. Yeah.
So whatever the backstepping you have discussed here, have you incorporated any sliding mode concept? No, sir.
No. I have explained very naive, simple backstepping controller way. But here one can include the sliding mode concepts while designing the K1 and K2. You see the gains what we are fixing, just I randomly told for a full placement, other things. If we can use that K1 and K2, if one can be the linear, the another can be non-linear from the sliding mode, that will become a sliding mode based adaptive control, sliding mode based backstepping. I'm telling you all the new research areas which I should not tell. just I'm telling you that is one possibility of extending, combining these two techniques.
Yes, sir. That's why I got idea and I wish to.
Yeah. Those
Thank
gains
you,
can be, yeah. Let me see if there are any questions in the chat box. If not, then will there be any more advanced level FDP in the future? As of now, I cannot guarantee any in the future, but at least not within a month. If anything is there, I will let you know through this WhatsApp. I will keep this WhatsApp, group open. How to choose the values of that already been discussed. Audio is there. Previous portion is missing, but now the screen is visible. So I don't know. Yeah, I think now it's time to leave. So we'll meet tomorrow. So it's my sincere request, all of you, please attend tomorrow's session. Thank you all. Thank you.